Hello everyone, my name is Julian Torres and I'm pleased to talk about my work titled Synthesis, Characterization and Functionalization of Graphene Oxide-Based Nanoplatforms for Gene Delivery. Okay, why are we working on this? Cystic fibrosis, emphysema, hemophilia, and retinitis pigmentosa are some genetic disorders and acquired diseases causing severe damage. People suffering from these conditions are faced with complex diagnoses and unsatisfactory treatments. Recently, gene therapy has been projected as a promising strategy to treat those complex diseases. The idea of this approach may be to replace a distorted gene with a healthy one, or completing a missing gene to express the required functional protein. However, to reach an efficient delivery of genetic cargoes, a crucial challenge to be solved is the entrapment of these cargoes by endosomes, which eventually degrade them. To address the efficient delivery of genetic material, viral vectors have shown high effectiveness. However, they fail to comply with biosafety requirements as they induce immune undesired immune responses. So, non-viral vectors have gained attention, and particularly those based on the use of nanomaterials. Gold, magnetic, polymeric, and lipid-based nanoparticles are some nanocarriers that have recently been studied due to their relatively easy preparation and high throughput production with controlled size. However, much more efforts are needed to improve their efficiency for delivering cargoes. Specifically, endosomal escape is a desirability for these nanostructured systems. Recent works conducted at both chemical and biomedical engineering departments at Los Andes University have demonstrated that magnetic nanoparticles conjugated with buffering, a cell-penetrating peptide, exhibited highly potential ability to escape from endosomes in several cell lines. So the objective of this work is to extend this approach to other types of nanomaterials to obtain an ampler number of platforms for the rational design of cell-penetrating nanovehicles. Particularly, graphene oxide has recently emerged as a promising material because of its unique electrical and optical properties, high surface area, and emerging advances for each large-scale production with controlled thickness. Apart from the general physical properties mentioned here, graphene oxide has gained great interest because of its chemical benefits. The presence of carbonyl and hydroxyl groups on its surface give us the opportunity to load proteins, peptides, drugs, and other cargoes of interest. Okay, now let me talk about the experimental approach followed in this work so far. Firstly, graphene oxide was prepared based on the modified Humer's method. Graphite sheets were oxidized under the action of potassium permanganate, sulfuric, and phosphoric acid. The mixture was stirred for 12 hours at 50 degrees Celsius. After that, the mixture, the resultant the reaction was quenched by rapidly cooling it down and adding uh, hydrogen peroxide. Next, the resultant graphite oxide was exfoliated to obtain a solid that was cyclically filtered, centrifuged, and resuspended in an aqueous solution of hydrochloric acid and ethanol. Finally, the solid was lyophilized. Next, graphene oxide was functionalized by rendering amine groups on its surface. To do this, the graphene oxide was dissolved in an aqueous solution and three reagents were added: tetramethyl ammonium hydroxide, acetic acid, and this compound abbreviated as APTES, which is an organosaline molecule uh, containing amine groups that were rendered on graphene oxide surface as shown in this figure. To characterize the nanoplatforms, infrared spectroscopy analysis was carried out. The infrared spectrum for graphene oxide, which is the black line, exhibit characteristic peaks for stretching vibrations for carbonyl and epoxy groups. After rendering amine groups, infrared spectrum could detect characteristic stretching vibrations for bonds such as silicon and silicon oxygen carbon. In addition, thermogravimetric analyses were conducted for graphene oxide, which is the black line, and functionalized graphene oxide, which is the blue line. Within this temperature range, graphene oxide lost more mass than the functionalized one. This indicates that the process of rendering amine groups increased the density per weight unit for graphene oxide. Additionally, the difference between both curves may indicate that the functionalization of graphene oxide was achieved with an efficiency of 38%. So taking together these results, we may confirm that graphene oxide has successfully been synthesized and modified with amine groups on its surface. Future work will be focused on conjugate buffering and conduct uptake assays. Also, we will determine inducible escape. To do that, we will label the vehicle with fluorescent molecule, and we will look for colocalization through confocal microscopy analysis. Now let me introduce my teamwork. Again, I'm Julian Torres, a PhD student in chemical engineering, and here are my co-advisor, Dr. Juan Carlos Cruz, adjunct professor from the Department of Biomedical Engineering, and my advisor, Dr. Luis Reyes, assistant professor from the Department of Chemical Engineering. Finally, I want to thank both chemical and biomedical engineering departments for their support in this work. Thank you.